Okay, so welcome to this next video in the playlist on G-protein coupled receptors. In this video, what we're going to talk about is the opioid receptors. Okay, so the structure for this video is we're going to start off by discussing the difference between an opioid and an opiate. Then what we will do is we'll discuss the 4 different types of opioid receptors. Then we'll turn our attention to agonists and antagonists for the opioid receptors. Then what we'll talk about is the in-detail molecular pathways by which the opioid receptors work. And then we'll talk about the function of the opioid receptors in analgesia. Okay, right, so let's start off then with the difference between the word opioid and the word opiate. Okay, so basically the concept of an opiate here is older than the concept of an opioid. Okay, an opioid is anything which activates opioid receptors. Okay, so these are anything which is an agonist for opioid receptors. Okay, and produces similar effects, therefore, to one of the major opiates, which is morphine. Okay, so agonists for opioid receptors. Okay, even more generally, an opioid is just anything which produces similar effects to morphine. Okay, through a similar mechanism, basically. Agonists for opioid receptors. Okay, whereas an opiate is something that actually has a similar chemical structure to morphine, basically. Okay, so not all opioids are opiates, and not all opiates are necessarily opioids. You can have structures which are similar chemically to morphine, but which don't activate opioid receptors. Okay, similarly, you can have proteins, for instance, which are opioids and activate opioid receptors, but they don't have any sort of similar chemical structure to opiates. Okay, right. So let's now talk about the leading example of an opiate, which is the drug morphine. And let's have a look at the chemical structure of morphine so that we can begin to get some appreciation of what opiates look like. We'll then see how the other opiate, which is heroin, is a similar structure to morphine. Okay, so morphine has a 5-membered ring structure. Okay, so it has 5 rings. It has 5 rings in its structure rather than 5-membered ring structure. It has 5 rings in its structure. Okay, and we'll begin with this one here, which is a benzene ring. So I'll put alternating double and single bonds. Then in the middle we have another 6-membered ring here, like so. Then another 6-membered ring off here, like so. Okay, and this isn't a benzene ring, but it does have a double bond, not there, here. Okay, so let me just scratch that off. Okay, then you have a 5-membered ring made up of these 4 carbons here, and then an oxygen off here, like so. Okay, and then you also have a 6-membered ring that's going to come off these 2 carbons here. So we've already got 3 members here. What we're going to do is add another 3 members in. So we're going to put another carbon coming off here. Now it's quite difficult to show this because in reality this ring would be coming out of the page towards us. But I'm going to show the next carbon here, then the next carbon after that here, and then there's a nitrogen making up the final member here. Okay, and this nitrogen then has a methyl group coming off it. Okay, so if we count the members of this ring then now, 1, 2, 3, 4, 5, 6. So that's another 6-membered ring. Okay, and I think this is the nicest way to draw this structure. Okay, now we haven't finished there. To complete morphine, you just add 2 alcohol groups on, 1 here and 1 here. Okay, right, so we have drawn a skeletal formula. So in skeletal formulas you don't show carbon atoms, instead you implicitly show them by corners, basically. So wherever you have a corner or where you have lines meeting, like this one here, that is an implied carbon, basically. Okay, you do show all other atoms than carbon except hydrogen atoms coming off carbon atoms. So for instance, when we look at this carbon atom here, we would have 3 hydrogens coming off that, but you don't show them because we're drawing a skeletal structure. Okay, so this is the skeletal structure for morphine then. Okay, so other opiates will have similar structures to this. So let's talk about heroin, which is the other very famous opiate drug. Okay, heroin has another name. It's also known as diacetyl morphine. Okay, and for short, diacetyl morphine can be abbreviated to diamorphine. So you take the di and then the A and abbreviate this then to diamorphine. Okay, so diacetyl morphine or diamorphine. This is what heroin is. Now basically, in the structure of heroin, what you'll then have is 2 acetyl groups coming off these alcohol groups. So basically, if we want to redraw this structure as heroin, so let's just revise our structure of morphine then. So we'll start with this 6-membered carbon ring in the center. Then we've got this benzene ring coming off the side here. Okay, with a double bond there, double bond there, double bond there. We've got another 6-membered ring over here, like so, with a double bond there. Okay, we've then got this special 6-membered ring that comes out of the page, like so, with a nitrogen in the middle there, with a methyl group coming off it. Okay, and then we have this 5-membered ring down here where we have an oxygen joining that carbon and that carbon. Now, in heroin, to turn morphine into heroin, what we're going to do is acetylate these 2 alcohol groups. So we're basically going to take the hydrogen off and we're going to add acetic acid molecules on. So let me show you the structure of an acetic acid molecule. So basically, acetic acid is the old name for ethanoic acid, the 2-carbon carboxylic acid. Okay, shown here. So this is what officially should be called ethanoic acid, but the old name for it is acetic acid, and people generally still use that. Now, if you remember from chemistry classes, basically carboxylic acid groups, like this group here, can react with alcohol groups. Okay, so what you can do is take the alcohol group off the carboxylic acid group, take the hydrogen off the alcohol group, bind those together to make water, and then bind this carbon of the carboxylic acid group to that oxygen, like so. Okay, so what you'll get then is the carbon of the carboxylic acid group linked to this oxygen of the alcohol group. This carbon then also has the double bond to the oxygen atom, and then it also has a methyl group coming off like so. And you're going to do that twice because we're talking about diacetyl morphine. It's going to have 2 acetyl groups off. So it's also going to have another acetyl group off this alcohol group over here, like so. Okay, so that is how you convert morphine into heroin, basically. And we can see that heroin therefore has a very similar structure to morphine and therefore can be considered an opiate as well. Now, where does this terminology of opiate come from? Well, basically, it owes its name to an even older name. Okay, so the oldest name is then opium. Okay, now opium basically is the name for an extract that you can get from poppies, which contain naturally occurring opiates, basically. For instance, morphine is a major component of opium. Okay, now opium comes from the poppy Papaver somniferum. Okay, so Papaver somniferum is the Latin name for the poppy that produces opium, Papaver somniferum. Okay, right, so that's an introduction to where this nomenclature of opioids, opiates, opium comes from, basically. Okay, right, so we're going to be interested in opioids, the agonists for opioid receptors. Okay, so let's now talk about the opioid receptors themselves. So basically, the opioid receptors are G-protein coupled receptors. They are examples of the G-protein coupled receptors. So we need to firstly discuss a little bit about G-protein coupled receptors, and then we can move on to talk specifically about the opioid receptors. Okay, right, so G protein coupled receptors, which are often abbreviated to GPCR for short. Okay, and G protein coupled receptors also have a number of other names, okay, so they're often also called 7 transmembrane receptors, or 7TMs for short. Okay, so we've got these multiple different names for G protein coupled receptors. So let's now discuss the structure of G protein coupled receptors. So if these two lines represent the outer and inner leaflet of the phospholipid bilayer, okay, so remember the cell membrane consists of 2 layers of phospholipids. It consists of the outer leaflet of the phospholipid bilayer and also the inner leaflet of the phospholipid bilayer, and these two are bound to one another basically. Now, in the phospholipid bilayer, you have implanted a G protein coupled receptor, and G protein coupled receptors have a structure that looks kind of like this. Okay, so they have 7 membrane-spanning alpha helices. That's their characteristic feature. And then their amino terminus is on the extracellular side, which is this side of the membrane, and then their carboxylic acid terminus is on the intracellular aspect of the membrane. Okay, so basically the membrane-spanning alpha helices are labelled according to their order going from the amino to the carboxylic acid terminus. So this first one here is called transmembrane domain 1, and for short, transmembrane domain 1 can be abbreviated to TMD1. Okay, then we have TMD2, transmembrane domain 2, transmembrane domain 3, TMD3. Okay, so I'll just write out at least once what this stands for. So the T is for trans, the M is for membrane, and then the D is for domain. Okay, and this just means these membrane-spanning alpha helices. So then you've got transmembrane domain 2, transmembrane domain 3, transmembrane domain 4, transmembrane domain 5, transmembrane domain 6, and then finally transmembrane domain 7. Okay, right. Now you also have these loops between the transmembrane domains. So you have 3 of these loops here that are on the intracellular side. So 1, 2, 3. And these are labelled up intracellular loop. And for short, intracellular loop can be abbreviated to ICL. So the I is for intra, the C is for cellular, and then the L is for loop. Okay, so you have the first intracellular loop, which is this one between the first transmembrane domain and the second transmembrane domain, and this will be called intracellular loop, or ICL1. Then you have the second intracellular loop between transmembrane domain 3 and transmembrane domain 4. This will be called ICL2. You have the third intracellular loop between transmembrane domain 5 and transmembrane domain 6, and this can be abbreviated to ICL3. Okay, so that's the nomenclature for the intracellular loops. There's a similar nomenclature for the extracellular loops. In this case, it's just ECL. So you change the I to an E because you've changed intra to extracellular loop. Okay, so this one between transmembrane domain 2 and 3 will be called extracellular loop 1. This one between transmembrane domain 4 and 5 will be called extracellular loop 2, and this one here between transmembrane domain 6 and transmembrane domain 7 will be called extracellular loop 3. Okay, so that's just a little bit of nomenclature for the different portions of the G protein coupled receptor. Finally, this portion that's prior to transmembrane domain 1, that will be called the amino terminal. Okay, and then this bit down here, which is after transmembrane domain 7 here, this will be called the carboxylic acid tail, or the C-terminal tail. Right, okay, so let's now talk about the classification of G protein coupled receptors. So basically, in the human genome alone, there are over 800 G protein coupled receptors, which makes them by far the biggest family of proteins in all of biology. Okay, they are massively used by nature. We do not understand why this 7 transmembrane domain structure is so special, but nature seems to have found it found that it was brilliant and just latched onto it and run with it, basically. But we don't understand what the significance of the 7 transmembrane domains is, but there seems to be something fantastic about having 7 membrane-spanning alpha helices because it has been used so much, okay? And these sort of receptors, you know, they are the main type of receptor that is used in the human body, okay? And around 30 to 40% of the drugs that clinicians currently use are acting via interfering with G protein coupled receptors. Okay, so vastly important family of proteins. Now, there are 800 or over 800 members of this family. So how do we begin to understand that? Well, we have to classify them into families. So there are 5 different families of G protein coupled receptors. So I want to discuss these with you now. Okay, so the 5 different families of G protein coupled receptors then. So family 1, which is the most important family, is the rhodopsin family of G protein coupled receptors. Okay, now this is easily the biggest family of G protein coupled receptors. Okay, there are over 750 members in this family alone. So 750 out of the total 800 G protein coupled receptors are in this rhodopsin family of G protein coupled receptors. Now, what's special about the rhodopsin family G protein coupled receptors? Well, basically, they have very short amino terminals and very short carboxylic acid terminal tails. Okay, so their main important portion is this 7 membrane-spanning alpha helices and then the intracellular and extracellular loops. And basically, the characteristic feature that you need in order to be a rhodopsin family G protein coupled receptor is that you need to bind your ligand in the transmembrane domains, basically. So the characteristic feature of all rhodopsin family G protein coupled receptors is that the ligand for that G protein coupled receptor binds to residues that are within the 7 membrane spanning alpha helices. Okay, so I've drawn it as though the ligand is specifically binding to the 3rd and 4th membrane-spanning alpha helice. In reality, it can bind to many different ones in the case of different receptors. Okay, so it's not a hard and fast rule that they bind to the 3rd and the 4th membrane-spanning alpha helice. The hard and fast rule is that the ligand binds to residues which are within the transmembrane domain. Okay, so most G protein coupled receptors are within this family. All of the opioid receptors are going to be within this family. Okay, right. Now, I do just want to mention the other families, even though this is the main family which is going to be important for our discussion of opioid receptors. Okay, but for completion, I do just want to talk about the other families. So the other families that you have the secretin family of G protein coupled receptors, okay? And basically, these, this family contains, for instance, the receptors to calcitonin, the receptors to parathyroid hormones. I'll give these examples. So the receptors for calcitonin, the receptors for parathyroid hormone, PTH for short. And also another important example is the receptor for glucagon. Okay, so all of these receptors basically fall into this family of secretin family G protein coupled receptors. Okay, now what's the significance here? Well, if you look at all of those ligands, calcitonin, parathyroid hormone, and glucagon, they are all proteins, okay? And that's the general rule, that the ligand for secretin family G protein coupled receptors is generally proteins. Now, that's not the feature that characterizes this family, though, although it is a true principle. Okay, the feature that actually characterizes them is that they have a large amino terminal domain, which I'll show in a moment because I haven't shown it yet. Okay, and basically, the ligand for these secretin family G protein coupled receptors binds to the G protein coupled receptor between the amino terminal domain and the transmembrane domain. So it will bind in here, basically. So I'll highlight that in turquoise. So this turquoise line represents the ligand basically, and you can see that it's binding between the amino terminal domain up here and the transmembrane domain here. Okay, so this is the ligand. Okay, so that's the characteristic feature of secretin family G protein coupled receptors, that the ligand binds between the amino terminal domain and the transmembrane domain. Okay, so that's the secretin family G protein coupled receptors. Next family up is the glutamate family of G protein coupled receptors. Okay, so examples of receptors which are in the glutamate family of G protein coupled receptors are the metabotropic glutamate receptors, often abbreviated to mGluRs for this M here is for metabotropic. And another name actually for G protein coupled receptors in general is the metabotropic receptors. Okay, so this means the G protein coupled receptors, glutamate receptors. Okay, so those of you who know anything about glutamate receptors will know that glutamate receptors are not usually G protein coupled receptors. The main glutamate receptors, and I'll put that main in quotation marks, it's fair to say that the main glutamate receptors are not metabotropic glutamate receptors. They are instead ligand-gated ion channels. So glutamate is the main excitatory neurotransmitter within the brain. Now, it governs fast neurotransmission within the brain, okay, and it works via ligand-gated ion channels. So, for instance, the AMPA receptor, the NMDA receptor, the kainate receptors, they are all ligand-gated ion channels, not G protein coupled receptors. But there are these other forms of glutamate receptors known as the metabotropic glutamate receptors, or mGluRs for short, which are G protein coupled receptors. Other examples of glutamate family G protein coupled receptors are the GABA B receptors. Okay, so glutamate is the main excitatory neurotransmitter within the brain. GABA is the main inhibitory neurotransmitter within the brain. And again, GABA usually acts through ligand-gated ion channels. Okay, so the GABA A receptors are cis-loop ligand-gated ion channels. Okay, and they're the main type of receptor for GABA. However, you do also have GABA B receptors, which are G protein coupled receptors, and they are again in this family of glutamate family receptor G protein coupled receptors. Okay, now what characteristic feature do all the members of this family share? Well, basically, again, it's the amino terminal domain that's special. So basically, the amino terminal domain of glutamate family G protein coupled receptors has this special domain that is called a venous flytrap domain. Okay, so this is what I'm showing here. So this is a venous flytrap domain. Okay, and the reason it's called that is because what happens is the ligand binds in between these two portions here. So this is the ligand binding, whether it's glutamate or GABA, okay, or it's something else. Basically, what will happen is when the ligand binds, these two domains close over the ligand and trap it in. So that's why it's compared to a venous flytrap, basically. And having one of these venous flytrap domains is what separates this family of G protein coupled receptors. Okay, so we'll call it there for this video and continue our discussion in the next video.